So we are starting a new session. This is satellite-based research, Geo-Science. My name is Ramaz Kotadze. I am from the Georgian Research and Educational Networking Association, GRENA. And our first speaker is Chris Atherton from GÉANT. Please, you have 20 minutes, if I understand correctly.
Thank you very much. Hi, everyone. So I was asked to talk about geoscience and satellite-based research, and every time I tried to give this presentation to some of my trusted colleagues, they kept coming back with the same question. So what? And in my mind, it's important. But that didn't seem to quite land the point. So I thought what I will do is to assemble the jigsaw pieces so that you can see why I think this is important from my perspective. So a good place to start is probably when I was born. On this little blue dot that is flying through space at the moment, when I was born, there were 4.5 billion people living on the planet. Today, there's 7.5 billion people. Every single person needs food and water. And this ball of rock contains every single resource we have ever used and ever will use until we colonize another planet. Of all of the available landmass, 16% of it is only capable of supporting agriculture. And so far, we've developed 13% of that. It's covered by 70% of water, but most of it is locked up in the poles. That's fresh water. Only 2.5% is fresh water. Of that 2.5%, 1% is available for us to use and consume every day. We live in a very delicate ecosystem, and humanity is having an effect on the balance of our planet. But that is unavoidable. And where humanity is concerned with politics and borders, animals, weather, nature does not respect borders. Earth observation allows us to see the world without borders. It allows us to see the change in the balance of nature over time. And there are many nations that are investing in Earth observation in order to tackle three big challenges. They are sustainable development, climate change, and disaster and emergency response. Now, sustainable development is easy to explain. It's what we leave for the future generations, the infrastructure that we build today that people will use in the future, and the resources that we leave them. And an example of this is with oil. So if you imagine how much oil is used for us to put this conference on, for us to travel here, for us to print things out, to use the plastic in the earpieces that we're wearing. We've already passed the point of peak oil production. Every single day, there will be less barrels of oil produced. That fuel source is running out. But Earth observation is not about the resources in the ground. It's also about the effects of the policies that our governments make on our planet. Earth observation allows us to see those government policies in action. One of those policies can be shown here. This is the Aral Sea. It used to be the 4th largest lake in the world. And because of a policy to promote cotton production in the 1960s and, from the 1960s onwards, this once thriving inland lake is now more like a pond in comparison. It produced 1/6 of the Soviet Union's daily fish catch. 40,000 people have lost their jobs because of the shrinkage of this lake. There's massive amounts of pollution being caused because the phosphorus, which lied at the bottom of the lake, has now been churned up by the wind because it's exposed. A desert has now been created as a result of these government policies. Now, the government of Kazakhstan is working really hard to try and restore this lake. There are ongoing projects to try and fix this, but it will take generations to fix. Earth observation also allows us to see climate change, the long-term change in average weather patterns. This image is the change in average surface temperature from 1950 to 2013 as a result of man-made emissions. This has a direct impact on the shrinkage of the ice caps and the rise in sea levels. This threatens low-lying countries like the Maldives and the Netherlands, and the Maldives potentially could be flooded within the next 20 years' time. They could be gone. Earth observation is not just about climate change and that, it's also about disasters, not just natural but man-made disasters. This is a refugee camp in Kenya. There are 450,000 Somali refugees living in this camp. 2 years previous, this land was empty. Earth observation helps us to prioritize where we place resources to help the most people. And that's what it all comes down to. Earth observation is about one big sentence. Better information leads to better decision making. And the global response to the 3 big challenges has been accelerating over the last 30 years because we've become more aware of the effects of population growth on our planet. But Earth observation isn't a new concept. There was this chap, Herman Potternick, who first prophesied about Earth observation in 1928. He said that an object in space could look down upon the Earth and try and measure in minute detail things which would be beneficial for mapping, science, and for exploration. And at the time, he was widely lambasted. But one of his ideas did stick. And in 1957, it came into being, and that was Sputnik. Sputnik was the first man-made satellite to orbit the Earth. But it wasn't just any satellite, it was also an Earth observation satellite. The radio signals used, that were sent out by Sputnik, were used by scientists to analyze the ionosphere. That was the first time we were able to see the world without a border from space. And it's been 62 years since Sputnik was launched. So far, there are over 8,000 satellites have been launched into space. There are about 5,000 that still remain up there. And of that figure, 710 of them are just devoted to Earth observation. That figure is growing by about 10% every year. That's a massive amount of data, a huge amount of data to try and spread around the planet. One of these Earth observation programs was called Landsat. So that started in the 1970s. And it was pretty revolutionary for the time. It had a resolution of about 1 pixel, which equaled about 100 square meters. But the data itself wasn't free. It was only until after the Kyoto Accord was signed, a year after the Kyoto Accord, sorry, in 2008, that the data became freely available. Before that, each image was worth $5,000 per scene. $5,000. The US government realized that all of the data that had been downloaded was actually worth more than building, launching, and operating the satellites for 20 years. They made it available freely, and the amount of downloads surged. It just goes to show the value of the data. And the main people that used this data were researchers and academics. Europe responded in turn to this in about 2014. They developed a new satellite program. This program, the data doesn't just come from satellites, but also in situ data sensors. It's called Copernicus. It's Europe's eyes on the Earth. This program cost 6.7 billion euros, and it's estimated that it'll generate about 30 billion euros by 2030. All of the data is freely available. You can download it. And this whole presentation is an invitation to you to use this data, because it would be irresponsible not to use it when it's freely available. So I'll talk a little bit about where the data comes from. There's the in situ, which is, as you can imagine, on the ground, but you've also got the satellites. So Sentinel-1 is a synthetic aperture radar satellite. It measures the height of the ground. Sentinel-2 takes pictures of the Earth in different optical or spectra. There's about 13, so you can see how a plant is changing, or the photosynthesis that is taking place in a plant. And the other satellites do interesting things too, like monitor weather and also monitor pollution. So far this year, there's been about 65 petabytes worth of data downloaded from the Copernicus data center. And it's, as you can see, it's been increasing every year, and it will increase. But would it surprise you to know that none of the EAP countries feature in the top 100 destinations for this data? This is crucial data that's used by scientists for climate change research, for disaster response, to tackle those three big challenges, by governments to make the decisions that they need to make. GÉANT with DFN provide that 100 gig link into the Copernicus data center. All of the data for Copernicus goes across that link. GÉANT also disseminates the data via another service called EUMECAST. EUMECAST is a multicast service. It's only available to people who are connected to an NREN or who have a satellite link. You cannot get this information from a commercial provider, only through an NREN. The NREN community is at the heart of meeting the challenges that we all face. Now, the old way of doing things is to bring the data down to the scientist. And this is the way that the Earth observation community is mainly working at the moment, but there is a trend to move away from that. To move away from downloading the data and analyzing it locally on your laptop. Instead, we need to start to bring researchers to the data to analyze it together, with the data and the processing facilities and the data retention that goes with it. More data is being acquired that can be processed by one laptop alone. That's why we need to make this change. And tomorrow we're going to discuss some of the new concepts that are relevant for the field of Earth observation. So if you do come along to the workshop in the morning, you're more than welcome. But going back to Copernicus for a second. First off, we'd need to find the data. Then we'd need to download it, process it, and analyze it. This is the traditional method of doing things. So to find the data, we've got many different ways. I'm going to talk through a few of them very quickly so as not to bore you. We've got the Open Access Hub, the Collaborative Hub, and the DIAS, the Data Information Access System. So talking briefly about the Open Access Hub, it used to be called the Science Hub until the European Commission decided to change the name to Open Access Hub to make it more open for different, not just researchers, but for business as well. You go here, you create your account. You can download 2 files concurrently at any one time. It's also got an API, so you can create a batch script. So if you're clever, you can create multiple accounts and download multiple amounts of data at any one time, but please don't tell the European Space Agency I told you how to do that. Then, to process it, you'll need a piece of software called the Sentinel Access Platform, or SNAP. This is proprietary software developed by ESA, so that you can take that data, analyze it, and process it, and then start to do your analysis. The link's there. Once you've got the data and you've processed it, then you need to analyze it. And in the notes, if you download the slides, I've put links to lots of places that you can find all this information for how to learn how to analyze the data. Going back to the other ways of accessing it, you've got the collaborative hubs. So these are national mirrors, national copies of the central Copernicus dataset. This means a country that runs a collaborative hub, can host the data and have their own access management protocols. You can share the data as widely as you want. And for example, the Ukraine has recently signed an agreement with the EC to host one of the collaborative hubs. This is a great advantage, not just for Ukraine, but I'd propose for the region. Because you've got things like the Armenian supercomputing center and the data cube that's been established. And now you've got the Ukraine who has the data from Copernicus. It would be a great advantage to the region to work together, to collaborate, to create a system that would allow scientists to do research across borders with all of the data sets that are available. But that's just an idea. There's also the DIAS, the Data Information Access System. So this is a collection of 5 different commercial providers. This is the new way of doing things, where you have the data, the processing, and the storage facility all in one place. And it is commercial, so it's chargeable, but GÉANT is part of a project called the Open Clouds for Research Environments, OCRA. We're trying to make those 5 DIAS operators freely available for scientists. So if you're a researcher, you can sign up, get a voucher, and you can access the DIASs for free. That's money that's there, that's paid for, that researchers can use to do their research. And I'd encourage all the researchers here to take advantage of that. Again, download the slides, there's more information in the notes. Earth observation data and systems are getting better all the time. But the main point is that you shouldn't have to be a scientist to benefit from the results and the analysis of the data. This is an image of Yerevan and Mount Ararat that I downloaded last night when I was putting the slides together. And I realized it's hard if you don't know how. It really is not straightforward to get the data. And that made me realize the central point to this. We're not there yet. We are not there yet as a community. Systems are still evolving, and it's not easy for people who aren't scientists to benefit from this data so that decision makers can tackle the big challenges, so that we as citizens can tackle the big challenges. It should be as easy as clicking a button to see what the effect of an earthquake is like in our city. It should be easy to see how the crops are doing in the field next door to us at the click of a button. It should also be easy to see where the factories that are producing the pollution on our planet are located, not just in the world, but in our regions too. It should be that easy. That's why, for me, Copernicus is an opportunity. It's an opportunity for the research to be performed, the businesses to be created, the understanding that it'll take to challenge or to tackle the 3 big challenges of sustainable development, climate change, and disaster response. With this data, you can be a time traveler in a way. You can go back to 2014 and you can see the world in a level of detail that you'll have never seen before. Using Copernicus can give you the benefit of hindsight to see what the effects of government decisions are and how they've influenced our planet. It'll give us and our governments the information we need to make better decisions, to make a change, to address those 3 big challenges. We need to make systems better as a community, to make it so easy that we just click a button. Like with Eduroam, we just pull it out of our pocket and it works. Copernicus is the gold. We now need to refine it. 60 years ago, the first Earth observation satellite was launched. My question to you is, what will our legacy be in 60 years' time? Thanks very much.
Thank you very much for interesting presentation. Questions, please. Please.
Question about Thank you. My question belongs to technical, maybe some aspects of this. First question, it is to have connection to this site or database over GÉANT, or exist any channels accessible?
So the website is accessible from anywhere. You can be on your home network. You can be on an NREN network. It's accessible from anywhere.
What better?
Sorry?
What is better channel? Or
the order. So from the Copernicus data center, there is a connection to DFN, to the POP in Frankfurt, where GÉANT is hosted. That's a 100 gig link directly into the POP that's provided by DFN that we've purchased from them and then sold that to the European Space Agency. From there, it connects directly into the GÉANT POP in the GÉANT backbone at 100 gig, and then it's spread out across the world from there. So it's accessible from Australia and Canada and the US. If you're on a commercial connection, it still goes across that first 100 gig link. DFN have commercial peerings, and it goes out via the commercial peerings into the commercial internet at that point.
Thank you. And second question about what volume of the data must to apply for this elaborating these data about.
Sorry, could you repeat that?
What bandwidth need to...
What bandwidth? It depends how much data you want to download. If you wanted to download the whole data set, I think there's around 8 petabytes of data that's produced every year. So you'd need at least either a 1 or a 10 gig connection to be able to download the data. But as I said, if you're downloading individual scenes, each scene is between 8 and 1 gigabyte, depending on which type of satellite system you get it from. So you can download it on your, like last night I tried to download it in the hotel, and it was supposed to take 2.5 hours. So I ended up connecting to my server, which is based back home, which has got a 1 gig connection, and I downloaded it in 15 minutes.
Okay, thank you very much.
Okay.
Other questions? There's one question. Oh, okay.
Oh.
Hello. I can bring our examples. So in Armenia, just recently we have deployed so-called Armenian Data Cube, which was supported by the Swiss National Science Foundation. And this data cube covers the satellite images which are covering the territory of Armenia and the surrounding. And we are receiving daily satellite images both from the Copernicus and Landsat images. And in our case, as a small country, it's about, nowadays it's about 10 terabytes of information, but of course it is accumulated data. But my question is different. Do you have a team in the GÉANT that they are tackling in the analysis problems? Because to download the data, to pre-process the data, it's one thing, and then to go to the real communities to solve these problems, it's another thing. So my question, do you have such teams? If yes, we will be happy to collaborate, because we have such problems in Armenia.
At the moment, no, not that step. But that is something that I've had a discussion with a chap up there not too long ago, in fact, during the break, to try and do something about that gap between once you've got the data, moving it to the processing and the analysis type of phase. But I'm not an expert on that, so I can't really comment too much. But there is a person who will be able to answer that. If you speak to me after, I'll introduce you to him.
Շնորհակալություն, Աշոտ Միրզյան, սպառոնի էջեցման կենտրոնի նախագահն եմ, դուք շատ հետաքրքիր բան ասեցիք, listen?
Yeah, I couldn't understand, sorry.
Խնդիրս որն է, Երևան քաղաքում ոչ մի բնապահպան Հայաստանում ու համոզված եմ ոչ մեկը չգիտի, քանի ծառ կա։ Ես խնդիր եմ դրել, որ մենք Երևանի ծառերը հաշվարկենք։
think it's Go ahead, sorry.
Listen. Ուրեմն լավ, կարճ ասեմ, խնդիրս նա է, որ Երևանում ուզում եմ հաշվառենք ծառերը։ Yerevan քաղաքի ծառերը ոչ մի գիտնական
It's not working, unfortunately. Do you have another one? If that's all right, yeah. Sorry to be a pain. If you wouldn't mind translating.
Դուք թարգմանեք թե ոնց է։ Ուրեմն Երևանում ոչ մեկ չգիտի ինչքան ծառ գոյություն ունի։ Խնդիր ունեմ հաշվառել ծառերը, ես մի քանի անգամ դիմել եմ մեր Երևանի քաղաքապետարանին, որ ծառերը հաշվառենք, գույքագրենք, ոչ մի իշխանության օրոք ինձ չհաջողվեց, ոչ մի գիտնական մինչև այսօր չի մտածում էլ դա անի, այսինքն նպատակը նա է open data ունենանք ինչքան ծառ կա, որ դա միջապես մենք բոլոր կարելի ասել երկրների շատերի հետ եմ շփվում շատ գիտնականների, սովորություն ունենք աշխարհը փչացնենք, հետո վերլուծենք թե ինչքան ենք փչացել։ Ես կանչի չհաշվառենք ինչքան կանաչ բնություն ունենք, որ ավելի զարգացնենք։ Այսինքն Կոպերնիկուսը կարա դեր օգնի կամ դեր միջոցով ինչ որ լուծումներ գտնենք, որ մեր ծառերը հաշվառենք։
In Armenia there is a real challenge in Yerevan. In order to calculate the number of the trees that are available in the territory of Armenia. And in this regard, can the Copernicus data help in order to solve this problem, to calculate the number of trees in the territory of Yerevan?
Sure. Calculating the exact number of trees is going to be difficult, but what Copernicus can do can show you the available area of where the trees are located. It can show you the growth of the area and also the reduction. They use it at the moment. I've seen some use case examples in the rainforest to show deforestation over time. I'd imagine if you know what the average square footage is of an area, then you'd be able to extrapolate how many trees should be in that area, but then you'd need to follow it up with in situ data analysis to verify that the data is correct or the calculations that you've made are correct. Is that one working? Okay, thank you.
No, there is no more questions, so thank you once more.
Thank you.
Our next speaker is Javier Quinteros, probably. I am not sure about
Almost perfect.
Thank you. You have 20 minutes.
Okay, thank you. Good afternoon to everyone. Thanks to the organizers for the invitation. My name is Javier Quinteros, and I'm working in Germany, in Potsdam, at the GEFZ. It's a Geoforschungszentrum, that is an institute for the study of earth sciences. And particularly, I'm working in the working group of GEOFON, that it's related to seismology. Let me give you an overview of what we actually do some research at GEFZ and then focus on seismology and on some things that we've been doing, not directly the scientific results that we produce, good quality, but it's not the idea of the talk today. The idea is to see how can we establish collaborations with different Armenian institutions and how you can benefit also in the same way that we benefit already from collaboration with GÉANT and other European initiatives. First of all, these are the different research fields that we are working on at GEFZ, from geo-resources to planet Earth monitoring in the plate boundaries, for instance, working on hazard risk, natural disasters, reduction strategies, climate dynamics. It's not the main focus, but it's important also. And the big topic is also continental dynamics for us. If we go into seismology, that is what the group I'm working on is doing research. It's basically the GEOFON group. What is GEOFON? GEOFON is a working unit there that it's based on 3 different pillars. It consists of a pillar that it's a global seismic network, our data archive, and an earthquake monitoring. Then, apart from that, from these 3 pillars, crossing all the 3 pillars, we do a lot of software development for all this, and we provide training and outreach for different countries in the world, for a lot of students, but also researchers and technical people. And of course, we shouldn't forget on the right part, we provide a lot of data sets, open data usually, almost 95, 98%, to the users, to a big number of users. These are the people that are working there. You see the pictures below. So, in a nutshell, more or less, GEOFON is actually, as I mentioned, one of the pillars is a global real-time, high-quality seismic networks that consist of more than 100 seismic stations that we have all around the world, and then we run it continuously. They are permanent stations. We receive that data via satellite in real time with a delay of seconds, probably 1 minute or something like that. Then we are the largest seismological data archive in Europe. We have more than 3,600 stations, a lot of regional networks and seismological experiments, also that are not permanent. There are studies that they go to the field, they collect data for 2, 3, 4 years, and then they archive that at GEOFON. And what we call an extended virtual network with more than 1,000 stations. Those are the stations that we already have, the 100 stations, more than 100 stations, plus also some other stations that they open their data in real time so that we can read it in real time and detect automatically earthquakes. We actually are the fastest provider for earthquakes in the earth, in the world. To give you an idea, from the origin time of the earthquake, we are providing the magnitude already, the calculation and location in a lapse of between 2.5, 3 minutes to 8 minutes, 9 minutes. I mean, that means you have an earthquake, you need to wait for the wave to propagate till the station. The station needs to send the data through satellite. We need to collect all the data in Germany, Potsdam. We do the calculation and simulation. We verify that the data is actually okay and that it's not one station that it's just not working. And then at that moment, we can publish the result. The scope for us, as I mentioned, is to provide high-quality real-time data, but important here is to foster international cooperations. I will come back to that in a couple of slides. The number of stations and hardware that we have deployed all around the world I mentioned, and the number of events to give you an idea of what we are producing as open data is more than 6,500 earthquakes per year. And we send more than 200,000 notifications of earthquakes divided by category or region or whatever to SMS or mails or contacting people that actually probably live in a region that it's quite dangerous and they would like to receive notification about that. How to start with the collaboration? Well, how do we collaborate with other institutions from other parts of the world? Let's say that someone, seismologists here working at Armenia, have some funding to deploy some stations or do some experiments, and then they collect some data. They have it locally, they can process the data, they can work with that. What do they do with the data? Usually, that's very 80s and 90s, they keep the data in a local hard drive in your computer, in your server for your group of work. That was okay a lot of decades ago. That actually is not that sure, not that safe today. What we do today usually is to go to a repository, an official repository, that it provides long-term archiving of the data. And instead of reading that locally, you can still do that, of course, but then that data could be available to the rest of the world if you pretend that. And that's actually quite good because then you advertise your data, you're being recognized in the scientific community, you receive attribution, and we do that part of the work. I mean, you only provide the data to us, and we just host and provide all the services on top of that so that you can make your data available to others and receive attribution for that. There was a study from Vines and collaborators in 2013 and 2014. It was published in Nature Communications. That for a couple of branches in science, that's what is happening with the data after a certain number of years. Let's say you do a publication. Of course, you did it usually based on a data set. Then after 10 years, research say, hey, I would like to get that data set because I would like probably to check that or to further investigate on that. After 10 years, only 70% of the data is still available. After 18 years, half of the data has been lost. So that's why it's not a good idea if you collect your data, paid usually or funded or supported by some government usually, some public money, and then it will be lost. I mean, no matter how good you are, how much goodwill you have, at a certain moment, someone will retire, someone will move to another institution, data will be lost. So we work on the data archival against that, of course. We facilitate the access of the data. The idea is long-term archival. That's what we do usually. To give you an idea, we have more than 100 terabytes. Usually that's not considered that much, but what you should consider is that we are providing data sets for users through web services. Do you know how many data sets we provide per year? 100 million data sets per year to users. But those are not just files that it's easy to provide, like, okay, give me that file, and that's it, that's one data set. No, the system doesn't work like that. The system, we have a very standard and strict system in seismology in the community. The user decides exactly how the data set should be formed. The user will say, I would like the region of Armenia consisting of this square. Between this moment and this moment, they will create the data set, they will receive it immediately. We have 100 million of that per year. And we provide around of 270 gigabytes per day, and that most of that is in real time, that we receive from all around the world. We come back. This will be available, as far as I know. How do we do that? During more than 13 years, we have been working on a software product called SeisCom 3, that it's freely available for everyone, that we opened that to the community, and today it's being run at more than 400 places, from people that they do in seismology as hobby, to the CTBTO, I mean the big world organization just to control that nuclear weapons are not being used. I mean, we have a broad spectrum. This is free, of course. We have a huge community that is supporting this, and we provide training on this. And that's also another point of collaboration. For any country that actually is willing to use this, we always find a way to collaborate with different countries all around the world. I mean, sometimes countries provide some data, we provide some hardware so that the countries can provide some data, and then we provide also training for scientists. That could be in Germany, it could be here. I will give you more details on that. Why did I mention that 100 terabytes that we have today? It's not a lot, because when we talk about big data, usually we think, oh, there's a big volume. We see a wonderful, actually a wonderful example in the previous talk by Chris about 8 petabytes or 80 petabytes or whatever. I mean, we don't have that much data, definitely, and not at all. But when we go to the definition of big data, it's actually not only the volume, but it's what they call the 5 V's. It's the volume, but it's also the velocity. I mean, even if you have 8 petabytes or 10 petabytes, or even if you have 2 megabytes, whatever, I mean, for some applications, you really need the data fast. That's where usually GÉANT comes to help you, of course. We've seen that also during the morning in the talk, with good links, good communication, real-time communication, transferring a lot of data. But also on the veracity of the data and the variety of the data. But we work in particularly in a lot of real-time data. As I mentioned, 100 million data files created on the fly and received synchronously. Well, then you need a lot of velocity to process the data. But we do collect a lot of data. Usually we've experienced a revolution in seismology because the sensors became cheaper, really cheaper. I mean, if you compare the prices of the computer 30 years ago with a Raspberry Pi today, then you see the difference. The same thing we are experiencing in seismology. But not only that, well, that of course means that we receive a lot of more data, and you will also receive a lot of more data as users, or you will produce a lot of more data because the sensors are becoming cheap. But we have also another source of, let's say, big volumes of data, that is fiber optic cable. Previously, until today, yesterday, 1 year ago, 2 years ago, usually you had to go to the field, deploy a seismic station there. That's what we do nowadays. And then you produce data at one point on the world. Today you can use normal fiber optic cable that actually we have in every single city, everywhere. And then installing some repeater, they call it interrogators, that's a weird name, you must confess that. On the fiber optic cable, you could have the equivalent of a seismic station every 2 meters of the fiber optic. Just to give you an idea, this is the resolution that you would have in an experiment with broadband sensors, seismic stations. This is 100 times less of the resolution that you would have for a fiber optic, because actually we had to reduce that 100 times because we couldn't plot it here. And that produced a huge amount of data, of course, now. And this is brand new, and then we will move in the direction of the previous talk. And you will also move on that, because of course, then you will realize that you need less money in order to collect seismic data because you have already a lot of fiber cables there. Let me show you another example of big data that we have and how we are working with that, particularly with real-time, how to detect. I said that we are the fastest agency in the world to detect earthquakes, and I said about 2 minutes to 7 minutes, 8 minutes. With collaboration at EMSC, what we are doing is EMSC is checking now social networks. EMSC is checking Twitter, some hits in web pages, different things, usage of applications related to earthquakes. They're using the location there, and when they realize about some abnormal traffic, they contact us in real time, and they ask for unreliable, not still published earthquake information. Some earthquake information that we are still waiting for a couple of minutes to see if it's really worth to be published. But they already detected that something really weird happened at some point in the world, and they can tell us, and we provide that information, and then the merging of these two technologies or two approaches, we fusion that, we merge that, and we improve a lot even the performance that we had it. We can see here, this is the performance of EMSC. Usually it's pretty, let's say, pretty slow, poor EMSC. They do a great work, but we've been doing much better. This is the amount of minutes that you need, the delay. We are much, much faster, but when we combine both, we can go up to 1.5 minutes after origin time, because we don't need actually the waveform to propagate till the seismic stations. We have one person multiplied by thousands or millions standing on the earthquake, and they can tell us even before the seismic station. That's also big data, and for that also we and everyone would need really good links and communications. Another example that we've been working on actually based on some services provided by GÉANT, that it's EIDO Gain basically. Everyone knows EduROM. EIDO Gain is more or less kind of the same approach. I'm trying to do it really fast so that I can use only my 20 minutes. But ask anyone at GÉANT, I mean, this is really amazing. But the idea is not to provide the Wi-Fi access, but to provide you the service of authentication worldwide. What we are doing actually, we've been creating in the last years a federation of data centers in seismology. And in order to do that, as we have global users, we don't know them at all, and considering the privacy regulations in Europe, we don't want to have user lists, that for sure. We really don't want to do that cumbersome stuff anymore. The best way to do that is to link to the EIDO Gain approach through some services provided by services provided by European Open Science Cloud, in particular in the European Open Science Cloud Hub, that it's a project that we are collaborating also with. We did a first prototype at UDAT, and then we used that in order to authenticate and authorize global users that we don't actually need to know. We only need that IDO Gain knows them, and IDO Gain knows most of the scientists all around there. So if we move to data management to start already the last part of the talk, what we provide and how you can benefit from the work that we are doing is that we can really take care of all the things that are not science. I mean, you can collect data. If you're a seismologist working in an Armenian institution, you can produce a lot of data. You can contact us. You can give us the data. We take care of the long-term preservation, high visibility at the global scale of our data to provide you with DOI for your data so that you can be cited and attributed for the work that you've done. You don't need to publish a paper. I mean, you can, before that, you can have a DOI already to be cited. We do the quality control, we do all the data management, we integrate into international initiatives, all with your data on your behalf. I mean, you're still the author, you still receive the credit, everything. And we put the data, of course, ready to be used for big data projects. I will skip this. Another way to have a successful collaboration usually with us at GEOFON is the usage of the capacity building and outreach that we are providing. I mean, it's not that we are working just for us. I mean, we usually, everything that we do, we go and advertise it everywhere. We provide that for free. That's our way to do the things. Open data, open software, open services, and open training and capacity building. I mean, for instance, we have every year international training course on seismology, 4 weeks. For students, completely paid. There is students, or it could be PhD students, it could be postdocs also, or some scientists, usually from underdeveloped countries, like the country where I come from, Argentina. I mean, we have a lot of students applying for that, but we do a really good selection, like 30 students every year, and we run that training course every 2 years in Potsdam, in Germany, at GEOFON, but the other years, that is in 2020, 2022, in the even years, I mean, somewhere else in the world, Ghana, Jordan, Myanmar, whatever. It was in Italy once, it will be in Argentina, I think, the next time. So, if someone from Armenia is willing actually to host that, this is a really good initiative that actually creates a huge community and gives a lot of impulse to the activity. We've seen that in the last 15, 20 years, a huge push to the activity at the country hosting that. I mean, and we cover a lot of the cost, of course. I mean, usually the local hosts provide only the logistics and the support. And of course, they receive a lot of students that can attend there, the course. So I mentioned already possible fields of cooperation. Also, another one that I haven't mentioned, but it was more or less present during the presentation, it's the deployment of seismic stations, normal seismic stations here. For that, we even provide the hardware. If we find a suitable place at Armenia, we provide a seismic station usually, or we provide what it's needed. We give the capacity building and the training for the people, local people here, so that we can do probably together the deployment, and the station can be just maintained by you. And that's your data, we share the data, and then it's a way also that you have local data, local seismological data and monitoring here also in Armenia. In things, we have global networks, but you could have local interests on that, for that data. Also, I mentioned the capacity building, the data management, and the support for SEISCOM3, that it's free. And the scientific cooperation of commonly acquired data. Important to identify from here, of course, always is two key people that are actually willing to be the link to provide these collaborations. And for us, that it's very important, the commitment that on the partner side, there will be also a big commitment to open data and to have open software development and things like that. It's not that we are going to collaborate so that we sit on top of the data and no one takes a look at that. That's not the way that we work usually. I think that's it, and that should be more or less 20 minutes. Thanks a lot.
Questions, please.
I have a small question in order to understand the European landscape. As far as I know, the NERIS is the core seismological infrastructure responsible for the seismological devices and infrastructure. Orpheus, it's more policy and, I don't know, administrative. And EPOS, it's a S3 project. And what is the role or relation of Geophone between EPOS, Orpheus, and NERIS in order to understand?
Yep, good. That's a good question, actually. Orpheus, originally, it was the origin of Orpheus. It was like a federation of data centers from the political point of view in order to have common policies, common data quality procedures and things like this in order to homogenize more or less a seismological activity within Europe. But that was kind of formal or based on policies. Geophone actually what did is to start the technological integration in that. Geophone was played a leading role in order to collect most of the data centers or countries within Orpheus in order to form a technical federation so that the user actually has no idea where the data is located, because the user actually doesn't want to know if the data is sitting in Germany, if it's sitting in Turkey, or if it's sitting in Romania. The user wants data from this station, and they don't care. That was more or less the development of SEISCOM 3, also related to that Geophone did, in order so that anyone today can provide data. The users really don't need to know actually where the data is sitting. They don't need to know that the data is sitting in Germany. They only need to know that the data, for instance, has been provided by Armenia. They don't really need to know us. They need to know the producer. And that's the role that Geophone had actually and has within Orpheus and EPOS is even on top of Orpheus. EPOS will try to merge Orpheus with other disciplines that are not seismology. But the thing is that EPOS is taking seismology as the most advanced example of this type of integration.
I've got a question. You mentioned the sensors that were located in the transceiver stations on the fiber optic. Are you working with commercial providers or anyone else in order to try and install those?
Yeah, actually, that's a good question. As I mentioned, this is a disruptive technology. It's quite new, and the comparison with broadband sensors is impressive. It's really nice, but there are still some details. Even in a conference, I met one of the specialists in this field worldwide, and I mentioned exactly what are you measuring here, because you don't measure velocity of acceleration, you measure strain of the fiber optic. And he answered me, well, we have no idea still what we are measuring, but actually it's showing everything that we would like to see. And that's very impressive. And by the way, it's a lot of data, we don't know what to do with the data. Now, but that's why we established cooperations also with telecom and other companies, so that they provide also the engineers, and we are doing first tests on cities, but we provide the fiber cable, because of course the next step will be, okay, there are fiber cables everywhere. What about the privacy?
Yeah.
So we are trying to be really conservative on that.
One of the reasons I ask is that GÉANT is in the process of redesigning the network and buying new fiber, and it might be worth having a conversation to see if we can try and help you with that.
Exactly.
Yeah.
Exactly. Definitely.
Cool. Thank you.
So I want to understand some technical issue. You have seismograms stations collecting information, and you are publishing information about EPO center or hypocenter, time, etc. And when you are calculating, when you are solving this inverse tomography problem, seismic tomography problem, okay, then you have to have some information about the earth core structure. This is very local issue. So if you are doing things for Armenia, then you have to have this information about Armenia. Do you use it? Do you have this information or not?
That's a good question. Actually, what we focus on is on the fast provisioning of the epicenter of the earthquake, and the magnitude calculation plus how the displacement was, what we call the moment tensor, if we have a lot of information. That's the only thing that we are using, and actually, as I mentioned, we are using data from a lot of stations that don't belong to us, and what we do is we agree with the partners, okay, we read your data, we use it to produce the earthquake parameters, the event parametric data, the epicenter, magnitude, and the depth, and the moment tensor, and then we don't use anything else. And we don't even store it. We store it for a couple of days or 10 days just to rerun it in case that we need to correct something, but no more than that. We only store or archive information from partners that they explicitly say, this is my data, take it, archive to the long-term preservation. Otherwise, we don't do that. The only thing that we share, and we also tell in advance to the people providing the data, instead of sharing with EMSC, for instance, that is the European initiative to concentrate the earthquake parametric data and the magnitudes and everything, we don't share the waveform, we just share the point where the primary wave, the P arrival and the secondary wave arrival. That it's basically, it's a minimum information that it's nothing almost. So we don't use, we have a lot of respect on the data that we collect. And we throw it away, actually, unless it's explicitly written in a manifest of understanding. Yes.
I think it does.
Listen. Իսկ ինձ հետաքրքիր է դուք եթե ինչ ճիշտ են թարգմանել, ասեցիք միջև 1.5 րոպե ճշտությամբ, այդ խնդիրները ինձ հետ են առաջանում են գրոտ, Listen, understand what I say. Repeat my question in Armenian or not. Listen what you say. Okay, I understand. But you listen. Okay, դուք ասեցիք եթե ես ճիշտ եմ հասկացել, բերեք ես ասեմ դուք թարգմանեք։ Դուք ձեր ելույթի մեջ ասեցիք, որ մինչև 1.5 ճշտությամբ RealTime, եթե ես ճիշտ եմ հասկացել թարգմանությունը, տալիս եք ինֆորմացիա։ Կամ լավ, դա այդքան է, կանչ 1.5 կամ վայր դուք ո՞նց եք ստուգում ձեր գործընկերներից այդ ինֆորմացիան։ Ինչքանով է դա ճշգրիտ, որովհետև դուք ասում եք կարող է մինչև անհատը այդ ինֆորմացիան տրամադրել, մենք տարածենք, բայց կարող է այդ մարդիկ կեղծ ինֆորմացիա տալիս, տերորիստը ուզում է միտեղ վնասի, ո՞նց եք ստուգում։ Որովհետև դա շատ վտանգավոր բան է, ո՞նց եք ճշտում ինֆորմացիան։
So you say that you can provide the information after 1 or 2 minutes to the end users, but there is a critical question how you check the information. Maybe it's a fake information, maybe it's not relevant information. How you check the information before to provide it to the end user.
If you relate to the information that we receive from the stations, usually we have a direct satellite communication from the stations. I mean, that's something that we test. And we have private networks on that. It's not that the data is available, just it's flowing publicly through open channels. I mean, the communication to the station should be explicitly allowed. I mean, that's like kind of, it could be think as an HTTPS connection, something like that, something that is secure end-to-end point. What we actually could have, and that's why we are kind of conservative usually, it's that there could be wrong information because the station is not working properly. That's why we check that with the rest of the stations around that. Yes, that we double check. That's why we improve in the case that I mentioned from the social media. We improved a lot that time because actually we had in advance the information to provide the magnitude and the epicenter. But we wanted to be conservative. But if the confirmation comes from somewhere else, then we, of course, we are faster.
Thank you very much.
Almost one.
I we need to move to our next speaker. Please, Valeria Catalano.
Good morning. My name is Valeria Catalano from GSA, that is the European GNSS Agency, and I'm working in the Market Development Department, where I am responsible for the timing and synchronization activities. And I will introduce my agency, the status of the Galileo and EGNOS programs, and the activities that we are performing on timing and synchronization. In particular, GNSA is the European GNSS Agency that is responsible for the market development and for the management of the European programs Galileo and EGNOS. We are located in Prague, where there is the headquarters. There are other facilities spread all over Europe, as for example, the Security Monitoring Center. We have 2 security monitoring centers, one in France and the second one in Spain. We have the service center, the Galileo Service Center, that is our interface with users, located in Spain. The reference center that provides an independent assessment of the Galileo performances, that is in Noordwijk in the Netherlands, and the EGNOS department that is in France, in Toulouse. As said, we have an European agency where our core activities are the market development, the security activities, the security monitoring control operations, and the Galileo and EGNOS exploitation. Regarding Galileo, the governance, what is the governance of Galileo? The European Commission has delegated to ESA, the European Space Agency, the space segment, while the GSA has in charge the service provision and the operations. Then, with a working arrangement between GSA and ESA, ESA is also responsible for the ground segments. Let's go on the side. So the 2 programs that GSA is managing are EGNOS and Galileo. EGNOS is the augmentation system, the system that augments the GPS. We have EGNOS has one open service that is free to users, with providing accuracy of around 1 meter. Then there is another service that is the safety of life, that is again with an accuracy of 1 meter, but it is compliant with the aviation standards and provide also corrections, data and information on the integrity of the signal. Then there is also an EGNOS data access service, EDAS, that is a network service that provides corrections via internet. And we can have, with this internet service, we can have accuracies that are lower than 1 meter. EGNOS has an European coverage, but it is under extensions in other parts, like other regions, like for example in North Africa. Galileo is the European GNSS system. It has different services. One is the open service that is free, accessible for the positioning, timing, and provide also the OSNMA, that is the Open Service Navigation Message Authentication. Then there is another service that is the PRS, the Public Regulated Service, that is just for governmental users. We have the Search and Rescue, that is the service that assists people that are in distress and inform with a return link that the help is on the way. And we have the high accuracy service. Also high accuracy service is a free service that provides an accuracy that is lower than 1 meter, is around 30 centimeters. And another level of authentication, that is the signal authentication service, that is based on the E6 signal code encryption. So is an authentication that for professionals user. So Galileo is the European navigation system. This is important to repeat, and is under civilian control, not under military control, as for example the GPS, and is full compatible with other constellations. The open service, but also the high accuracy service, is free, and provides the 3 different levels of authentication. I said are the open service navigation authentication, navigation message authentication, the PRS, and the signal authentication service. And these are the important differentiators of Galileo when compared with other GNSS systems. The status of the program. 26 satellites have been launched. 4 are in production and will be launched by 2020. In 2016, we declared the initial services, and now in 2019 we are testing the search and rescue, the PRS, but also the OSNMA, and we will start testing also the high accuracy service. While the full operational capability that will be operative from 2021, where 30 satellites will be in operations. And this is another slide just to highlight that 26 satellites are in orbit, but 22 are operational. The other one are under commissioning. And in this slide, you can see that we have the ground that is spread all over the world. But in Europe, apart from the GSA facilities, we have also 2 control centers, one located in Italy and the other one in Germany. Part of the ground segment is this timing service provider that I will explain in a few seconds, talking about the timing synchronization activity. So this timing service provider provides the offset between the Galileo system time and the UTC. And it's operative from January 2018. And 2 of them are installed in the 2 control centers. So, talking about timing and synchronization, as said, I am in the market development department, where the market development of Galileo and EGNOS is one of the core tasks of GSA. We have our activities are divided in 9 market segments. One is road, maritime, aviation, rail, LBS, agriculture, surveying and mapping, timing and synchronization, and also governmental segments. For all these segments, we develop the value chain. And to fulfill our main objective, that is to foster the Galileo and EGNOS penetration, our activity, our tasks are divided in 3 pillars. One is to understand the market and the user needs. Regarding the market, you can consult our website, where we publish every 2 years, alternatively, the market report and the technology report. Actually, the market report issue 5 is published in the website, but in next month, at the beginning of October, we will publish an updated version number 6. And for the user needs, we are constantly in contact with users to understand their needs and translate their needs in requirements. And in the last years, we also organized the user consultation platform, where we invite all the users divided in panel, where one panel for each market segment, where we interact. We present our market, our GNSS user requirements, and we interact to them to understand which could be the future evaluations of new services, new application, and what are their needs in terms of improvement for Galileo and for EGNOS. And another pillar is to stimulate the demand and the adoption, and also for these activities we are in contact with the receiver manufacturers, with the service providers, we are part of technical boards. And the last one is to create, pillar is to create an EU offer. In fact, we manage two R&D projects. One is the Horizon 2020, where we manage the GNSS project of Horizon 2020 that are focused on the application. And the other one is the fundamental element. It's another R&D project, but it is focused on the development of receivers and devices. When it comes to timing and synchronization, we know that timing and synchronization is an important, a crucial market. Is crucial because it is linked with the critical infrastructure. There is an European directive on the critical infrastructure where it's defined, the critical infrastructure is defined as an asset that is essential for maintaining vital societal functions related to health, safety, security, and social well-being of people. So, for this reason, telecommunication, energy, and finance are considered critical infrastructure. In telecommunication, GNSS is used for time slot management, for application are the SATCOM, are the PMR, the digital cellular network, and the public switched telephone networks. In energy, the timing and synchronization GNSS is used to measure the status of the networks and analyze fault along a transmission line through these phasor measurement units. While in finance, the GNSS is used for the time stamping of every financial transactions. And the main application are the financial transactions. It's a strategic market, but it's a very small market. It's 0.7 of the GNSS market, but is fundamental because of the critical infrastructure. And in the new issue of the market report, we renamed this market segment as critical infrastructure. So in this new version of the market, you will find this market segment as renamed as critical infrastructure. The market, the 19% of this market is composed by telecom. Is a stable market that is slightly increasing, in particular for telecommunication, for the deployment of the 5G, where we hope this could help to increase the GNSS penetration. And in finance, it's also slightly increasing, and there is now a new regulation, EU regulation, where it is needed for every financial transaction traceability to UTC. So also this regulation we think could help the GNSS, the Galileo penetration. And in energy, also energy is the market is slightly increasing, and this is due to the replacement of the smart grids, in particular in region as Asia. In Asia. As said, during the user consultation platform, we presented the user requirements that were endorsed by users, and you can find the user requirement for each market segment in the Galileo Service Center. I will show at the end of the presentation the link where you can download the user requirements, the user requirement reports. And we have worked a lot in the last years to foster the Galileo penetration, because in timing and synchronization we faced the two criticalities. The first one is that GNSS is mainly used as backup for the timing and synchronization, backup to terrestrial network. And then another problem is that the GPS is the main supported and used constellation, while analyzing all the timing and synchronization technology, we have seen that Galileo is the fourth supported constellation. So we had to work a lot to foster the market. We think that with the deployment of these authentication services, this will help us, because during the user consultation platform, we have seen that there is a great expectation on these authentication services by users, but the authentication will help to increase the market, but it's not enough. We have also worked on the application side. We have worked to develop some added value services that we renamed in a creative way application offerings, just to do not create confusion with the Galileo services, but in reality they are added value services that we would like to implement in the TSP, in the timing service provider, and we would like to provide through the Galileo Service Center, implemented in the TSP and provided through the service center. We have defined 4 application offerings. The first one is a time integrity that gives information on the validation of the performance of the Galileo signal, and we have seen that this application offering could be interesting for all the kind of users, but mainly the users from power grids and from finance. Then we have the application number 2, that is NTP distribution via remote audit, that is dissemination via NTP with an assessment of the client clock synchronization, providing audits and reports. And this one could be interesting for the financial operators, since now there is this new directive where the traceability to UTC is requested. Then we have another application offering that is named Certified Time Steering and Monitoring, that is at the receiver level and provide info on the offset between the Galileo systems time and the user terminal. This one could be interesting for the power grids operators. And the last application offering is a synchro service that we named the Robust Accurate Time service, that could be important for the telecom operators. So we have a plan to develop these application offerings that is based on a short term, for the short term on the open service, while for the long term we would like to provide this through the OSNMA or the commercial service authentication or the signal authentication service. Then on the receiver side we also launched a program that for the development of timing receiver. We are awarded 2 projects in parallel, and these projects are ongoing. So this was my presentation. I hope I gave a clear vision of our activities, but as a last slide, if you want to know if your any device is Galileo enabled, please consult this use galileo.eu, where you can find all the devices per market segment in the GSC website that is written there. Okay.
Thank you very much. If there is no questions, I would like to thank all speakers again for very interesting and informative presentation, and we close this session.